So what we're going to do is we're going to go through the solutions to the question 1 on the worksheet conservation of momentum. Of course, I would ask you to do this yourselves and take some time to do this in class, but I'm going to go through it so it shows how long it's going to take to do these questions if you could do them straight away. Obviously, some students might take longer, some students might take less time to do them. So question 1a says, object 1 has a mass of 3 kilograms and a speed of 8 meters per second. It collides with a second object of mass 1 kilogram, which is initially stationary before the collision and then sticks to it. Calculate A, the momentum of object 1 before the collision. So question 1a, momentum of object 1, P1, equals m1 times v1, which is equal to 3 multiplied by 8, gives 24 kilograms meters per second. Question B, the momentum of the combined masses after the collision. Well, the momentum of the combined masses after the collision is the total momentum before the collision. So this is the principle of conservation of momentum. Okay, we always start with this in a problem such as this. So this really helps us because we know that the momentum of the combined masses after the collision has to be 24 kilograms. It has to be the same as what it was before the collisions. There's no change in the total momentum. In this case, the total momentum comes only from object 1 because object 2 was stationary. Therefore, momentum afterwards is 24 kilograms meters per second, just like in part A. This shows how useful it can be because then we can start to discover what happens after the collision as well. So part C says calculate the speed of them after the collision. So if the total momentum, which is this, which we know because it's the same as the one before, the total momentum equals the total mass multiplied by the speed of the combined masses. So here we've got our equation that we're going to rearrange for the speed of the combined masses. So the speed of the combined masses has to be the total momentum divided by the total mass. You divide both sides of the equation through by the total mass. So this is your original formula, this is the rearranged formula, and then you do substitution. 24 divided by 3 plus 1. Where does the 3 plus 1 come from? That's the total mass. 3 of object 1 and 1 kilogram for object 2. 3 kilograms for object 1, 1 kilogram for object 2. So this gives us a speed of 6 meters per second. Question D, or part D, the amount of kinetic energy object 1 has before the collision and the kinetic energy of the combined mass after the collision. So the kinetic energy is a half mv squared, and we're talking about kinetic energy because we'll already have done kinetic energy. That will be something that is covered before we get onto momentum in the mechanics, but it's really useful to link it in with the momentum here because we can talk about collisions being inelastic or elastic. So the kinetic energy is a half mv squared. The students should know this equation, and so we do a substitution. Half times 3 times 8 squared, 96 joules. The kinetic energy afterwards would be a half mv squared. Half times 3 plus 1 times 6 squared gives 72 joules. So we can see that there's a difference between the kinetic energies before and afterwards. Therefore, kinetic energy, some of it is lost, and the collision is therefore inelastic. And I would suggest that the students would have completed questions 1a to 1c, and then these may be extension ones relating it back to prior learning, D and E. So E says, explain an energy transfer which would account for part of the change in total kinetic energy of the objects during the collision. So kinetic energy, some of it is transferred to heat and sound, some of it becomes or remains as kinetic energy of the combined object. So it remains as it's not all completely transferred to heat and sound. Heat is produced via compression when particles of the object collide, so like the squashing and of together in the internal